This meeting is now being recorded.
We are lucky today to have Areg Danagoulian from MIT with us. Last month we heard about a sort of a related set of work being done at Princeton, also trying to look at warhead verification with zero knowledge. And what Areg's going to tell us about today is work that he's been doing with some colleagues at MIT using a different methodology. So, Areg, please.
Okay. Thank you for introduction, David. Do you hear me well?
Yes.
Yes. Okay. All right. Okay. So all right. So before I talk about the actual project, which is the topic of this talk, let me make a quick introduction about the group of the researchers here in our department and about the lab where we're working. So the Laboratory of Nuclear Security and Policy has been set up in the Department of Nuclear Science and Engineering at MIT a few years ago to specifically pursue policy-relevant technological research in the area of nuclear security. So we work on various kind of topics that involve warhead verification, non-proliferation, enrichment, cargo security, nuclear detection. Some of the people, some folks might be familiar to you. Just there's about 3 faculty. There is myself. I've been here for the last 2 years, and many of you know Scott Kemp, who has been here for about 4 years, and Dr. Dick Lanza, who has been in this department has been working on this in this area, this general area, for about 30 to 40 years. We have a number of affiliated faculty that are also working with us. We have one postdoc, Brian Henderson, who started working with us a few months ago. He's actually funded by Stanton Fellowship, and we're actually looking for a second person. So if you know someone who might be interested in this kind of work, please let them know and ask them to apply. We have many students who are participating in this research effort. I'll point out Jason Warhead and Rory McDonald, who had a heavy involvement in this project and did lots of the heavy lifting that led to our results and developed many of the ideas that we're currently working with. That said, let me start talking about the actual project and the history behind that. Okay. So where do we start off? I'll start off with talking about the historic problem, the various kind of attempts at this problem, various kind of solutions that people have offered. What are the general kind of approaches, if you will, general frameworks in which people approach this problem? And ultimately, I'll talk about our contribution, what we have been working on as far as this is concerned. So to understand the history of arms control, specifically in the area of nuclear weapons, let's consider the most recent treaty, the New START Treaty, which was signed a few years ago between Barack Obama and Medvedev, the president of Russia, back then in 2011. It stipulated a reduction of deployed warheads from about 4,500 to 1,550 each for every country, which is a factor of 3 reduction from the previous numbers. And of course, it's a much smaller number when compared to the Cold War era numbers, which were in tens of thousands. Okay? So one question that immediately comes up whenever you talk about treaties, any kind of treaties, especially treaties involving something as important as nuclear weapons, is, well, how do people verify? How do the people verify that the opposite side or their partner country is actually pursuing its obligations and is actually doing what they said they will be doing? How do they actually count down this number of the warheads? So the short answer is they do not do that. They do not count the warheads, and we'll talk about it very briefly as to why they do not do that. Instead of going after the warheads themselves, they actually verify the elimination of the delivery vehicles. What's a delivery vehicle? It's anything that will carry the warhead or the weapon to its final target, to its final destinations. Okay? That means intercontinental ballistic missiles. It means submarine-launched ballistic missiles. It means artillery. It means cruise missiles, strategic bomber aircraft. So here are a few examples. For example, after the INF Treaty, which was the Intermediate Nuclear Forces Treaty in the late 80s, the Americans agreed to cut down, so the treaty stipulated the elimination of all the medium-range weapons, which means medium range means between 500 kilometers and 5,000 kilometers. And as part of that agreement, the Americans were going to liquidate all their medium-range cruise missiles. So how did people verify? Well, both parties sent to each other inspectors, okay, which went and which credibly verified that the opposite side is doing what they said they will be doing. So here's an example. On the left, there is a picture of a Soviet operative who is inspecting a Gremlin cruise missile before it has been destroyed. Okay. In the middle, there's a picture of a member of the Congress who's looking at one of the Soviet ICBMs before that is being destroyed. Okay. And then also after the START 1 treaty, the Americans agreed to cut down their fleet of B-52 strategic bomber aircraft. They agreed to destroy about 365 B-52s. So how did they prove that they have done that? They took this bomber aircraft, they dragged them to a desert in Arizona, they cut them down with actual guillotines and let them sit and dry in the desert for about 3 months until the Russian satellites flew over, took pictures, visually verified that yes, these bombers have been destroyed. And the general thing is that it's relatively easy to verify that the delivery system has been destroyed because it's kind of difficult to fake a delivery system. So, you can come and visually inspect that, say, the cruise missile is not made of styrofoam or wood, that is an actual, missile. And the visual verification is seen sufficient to, in fact, validate and, authenticate the delivery system and then confirm that, yes, it has been destructed, and then count that towards the opposite country's obligation under the treaty. Now, this is not such a bad approach when it comes to nuclear strike capability, because ultimately you can have many, many warheads, but what really determines your strike capability in a nuclear war scenario is the number of your delivery systems. If you have 10,000 missiles if you have 1,000 missiles and say 10,000 warheads, all that matters are the first 1,000 warheads. The remaining 9,000 warheads you cannot shoot at your enemy, so they're essentially useless. So the delivery systems have been a fairly good proxy for two countries' strength, nuclear strength. So why is this a problem? The problem is that this leaves behind very large leftovers of essentially surplus weapons, okay, non-deployed warheads. So non-deployed means, what does deployed mean for people who maybe are not exactly in this field? Deployed means something that is ready to fire. It's a warhead that's sitting on top of an ICBM, which can be launched in 10, 20 minutes. Okay. And non-deployed warheads, as a warhead in a stockpile, are the ones that are kept in bunkers as, if you will, for lack of a better word, as a spare part for the main warhead. In case you have any doubts about the main warheads, deployed warheads functionality, you can replace it one with a stockpile. So stockpile weapons also have to be functional. Okay. The problem with this state of matters is that you have the two countries have had fairly large stockpiles, okay, which is counted in thousands, even after the New START treaty. Okay, that leaves the door open for theft, which can lead to nuclear terror and to nuclear proliferation. And also, there is the possibility of rapid rearmament in times of political crisis. So the countries will reduce their delivery system count, and then in case of a political crisis, they'll quickly build up their ICBMs, their cruise missiles, and their delivery systems. So, this situation in some ways has been good in the past, but this is really not sufficient. And the question is that, can we come up with new treaties? Can we enable new treaties which will really go after the warheads themselves? Okay. So this abundance of, if you will, non-deployed excess nuclear weapons, is really something to be concerned about. Okay. The pun intended. Okay. So why don't we go after the warheads themselves? Why do we authenticate and verify the delivery systems? Okay, without, the answer is that, well, because we need to do that without revealing classified information. So you see a B-52 aircraft, you are fairly confident that this is a real thing. Okay. However, what does a nuclear bomb look like? So, I have to get used to this. Yeah, so here's an example of the warheads that go on the Minuteman missile. This is the delivery, what you're looking at is the delivery bus, which can carry about 10 multiple independently targeted reentry vehicles, MIRV for short, and effectively these are about 1.5 meters big approximately, and upon outside it looks like a black cone, quite literally, and it's very difficult to understand what's inside. It's difficult to understand because they will not let you look inside. If you truly, the best way perhaps to authenticate these warheads and say, yes, they are real before dismantling them is to open them up, cut them up, look inside, look at the components, and verify that, yes, this is a nuclear weapon. However, the two sides will never allow that to happen because in the process, the opposite side will find out a lot about their weapon designs, and that may allow them to, for example, develop some kind of improvement to their own, or they might may be able to develop some kind of, or at least optimize their countermeasures if they develop any. Okay. So the two sides will never allow the inspector crews to find out anything about their nuclear weapons designs, and they will never allow this to happen. Simply, they will not sign any kind of treaty. Perhaps an alternative, also unrealistic one, is to take these warheads, actually put them inside a borehole and detonate and verify that it was warhead. Of course, that's not going to happen either because of the test ban treaty. So can we come up with some kind of a measurement technique, some kind of a technology, which will effectively do some set of measurements on these objects and somehow verify the fact that they are warheads without revealing too much information to the inspection crew? All right, so this is a problem that people have worked on for quite some time. The nation labs have been very active historically. The US national laboratories, as well as the Atomic Weapons Establishment, UK, have really worked on this problem. And one method which was developed with one framework of approaching this problem was called the attribute verification systems. So attributes, what does attributes mean? Attributes really means a characteristic of a weapon. Okay, for example, its mass, its the mass of its plutonium pit or HEU, the high explosives or something else like that. But the additional things that was essentially developed, there was a concept of information barriers. The notion is that, again, you don't want the inspector to find out like small details about the diameter of your plutonium pit. But you do want someone to check that. So that checking process has been effectively transferred to an electronic device, which is called an electronic information barrier, which performs under the hood, performs a set of measurements. This could be either passive measurements. You could look at various kind of decay lines from plutonium and something else, and capture lines from high explosives, et cetera, or it can be an active method where you irradiate it with photons or neutrons, et cetera, et cetera. And then you have a set of detectors which collect data. Okay, they do some kind of data processing, data analysis with some algorithms. Humans are not involved in this. Then they do some kind of comparisons versus some very general criteria. Okay, and then they lit up green lights or red lights. So if you see all the green lights lighting up, basically the information barrier is telling you that yes, the measurements match some very general criteria. Now, this criteria has to be very general because, for example, criteria can be was the amount of the inferred mass more than 500 grams? Was the plutonium-240 concentration less than some amount? Was there high explosive present in this thing? Okay? You cannot have something which tells you the mass with a resolution of, say, 10 grams because that will be too much information. So you have to keep this criteria very, very general. So the notion is that because most weapons have plutonium mass more than 500 grams and say have explosives, then if the attribute system is telling us that yes, there is more than 500 grams of plutonium and yes, there is high explosives, then it must be a weapon, right? So I have a little bit of a cartoon version of this approach. Imagine I've got a box and there's a little bunny inside, okay? And this curtain over here is the information barrier system, which under the hood does its own checks and does some very general checks. And you want to verify the animal inside the box, in fact, is a rabbit. Okay? So it checks for these, for the ears. Does it have long ears? Yes. Does it have big feet? Yes. Does it have a furry tail? Yes. So it must be a rabbit, right? Because rabbit has all these things. Okay. Well, all right. So here's a picture of my own dog. Okay. It has long ears. It's a hound mix, so it has big feet. It can run very fast. It has a beautiful furry tail. Okay. So my dog would easily hoax this kind of system. Okay. The curtain or the information barrier will never be able to tell the difference between a dog and a rabbit because its checks are too general. So you sort of understand where the problem is. There's really a paradox. If you want something that is information secure, where it does not reveal too much information, then it means the criteria have to be very general, very broad. But by the same token, it means that the system is quite a bit hoaxable. And if you don't want to hoax the system, then you have to go for fairly detailed information. For example, for case of the rabbit, you could have the information barrier extract its DNA. And then you can truly verify this is DNA of a rabbit. But in the process, you might find out the actual length of its ears. You might find out its color, which says classified. And you might find out its explosive yield, which is also not allowed. Okay. So so you have basically the information bearers have significant advantages, or the attribute verification has significant advantages, but ultimately you have this paradox that you have to deal with, which is that you have to choose between information security or hoax resistance. And there's yet additional problem with the information bearers is the fact that all this is being done in the bearer itself is in electronics and software. And electronic software means millions of components, which are very difficult to verify. Okay? It's very difficult to do a unit test against malicious, intentional bug. Okay? So that leaves the door open for backdoors, hacks, software exploits, okay, which can lead to not only information leakage, but also one side can put various kind of like trapdoor functions, which will lit up all the green lights even when things are not matching. Okay. So, you know, this concept were developed in the 90s, and both Russians and Americans the Russians participated to this process. Actually, there was quite a bit of dialogue between the national labs and their Russian counterparts. Okay. But ultimately, they were not adopted for a variety of reasons. This was one reason. Also, at some point, there was no political will. So, what's an alternative to this attribute verification system? You can think of attribute verification as essentially like dead reckoning, where you are trying to measure things from scratch and make decisions from scratch. The alternative method, or alternative approach, I would say, is called template verification. And I just want to clarify when I say our research, you know, template verification has been also proposed has been pursued in the national labs, is pursued by many people. So the concept is not exactly ours. I don't want you to make, you know, that mistake. But basically, template verification is radically different from attribute verification because rather than doing an absolute measurement, you're doing a comparison. And any physicist that you talk to will tell you that comparisons are always easier, always preferable than absolute measurements. So people who come from, say, high energy or medium energy physics, you know, we love to measure, my background is in medium energy physics, we love to measure asymmetries, not absolute cross-sections, because they're so much easier to measure. I had to measure cross-sections for my PhD thesis, and that was, you know, quite a bit of a nightmare. So how do we start off by doing a comparison? What's the basis of doing a comparison? Okay. So what you do is you start off by an authenticated template. You get hold of a warhead that you actually know is real. Okay, let's call it the template or the golden copy, you know, to keep it colloquial, right? So, for example, the Warhead 88, you get hold of a golden copy. How do you do that? There's a few different ways of doing it. The one way is, for example, you can have an inspection crew that shows up unannounced to an ICBM site, like in Russia or vice versa, right? And they randomly pick a silo. You know, this is a surprise visit. They open the nose cone of the ICBM and they pick one of the reentry vehicles on top of the ICBM. Now, you're quite confident that that warhead is going to be real. Why? Because Russia's nuclear deterrence hinges on having real warheads on real ICBM. Okay. The idea is that essentially they would not compromise their nuclear deterrence by putting hoax warheads on their ICBM just for the sake of, you know, hoaxing the rest of the process. So now you've got your golden copy, and now what you're doing is that you go to some kind of a facility where the surplus W88s are kept. Okay, so this is red ones, obviously. And now you're doing a comparison, and there's still lots of complexity involved in that. But comparison means that you are comparing your A0, okay, with A1. Are they identical? Whatever that means, we'll see what that actually means. If they are identical, then what it means is that if A0 is authentic and if A1 matches A0, then A1 must be authentic as well. You do the same check on A2. You do the same check on A3. If they all match A0 within some kind of hopefully stringent criteria, then you know that these are authentic warheads. You send them to dismantlement, and you count them towards that country's obligation under the treaty. Okay, so easier said than done. I mean, question is, well, how do you do this comparison? Okay, so you have to come up with some kind of a protocol, some kind of a methodology, some kind of a process which does this measurement and meanwhile protects, you know, the secret information, okay, and does not rely on electronics or software. So preferably it has to be something which does the cryptography, because that's what information bearers are essentially. They're cryptographic systems. It has to do cryptography preferably in the physical process itself. Why physical process is better than electronic software is because verifying electronic software systems is fairly difficult. But the Russians or the Americans can trust their understanding of physics. If you can understand that the physics works the way it does, and then you can actually, based on physics, you can check and understand that, yes, what the opposite saying is true is probably true. Because we have physicists, they can validate this, they can agree that this is, you know, or disagree that this is true or not. At the same time, just like any kind of detection system, because this is also detection systems, it has to be able to catch hoaxes. Okay, if there's someone tries to slip in a hoax, you have to be able to see that. And it has to be able to catch type 2 errors, which is false positives or false alarms. Okay, you have to make sure that there are no false alarms. So if the hosts bring you an authentic warhead, you don't raise an alarm because you suddenly thought that it was a fake. So what do we need to use for this? And what we will be pursuing, as the title of the suggests, we'll be using NRF, which stands for Nuclear Resonance Fluorescence. Okay, but before going to NRF, let's talk about this general concept of physical cryptography, which I mentioned at least a few times. Okay. So very schematic, I want to keep this very schematic, very general, very abstract. So very roughly, one way to think of physical cryptography is that you have some kind of a signal, okay, which goes through some kind of a physical process and results in a new signal, which is a hash. And you want this physical process to be a sort of a one-way function, okay? And it's important that the hash is unique to the original signal. Okay? So if the signal changes, the hash will change too. Okay? And the notion is that if you have got two signals from two objects, and if their hashes match, and you use the same physical process, okay, then it implies that the original signals, that the original objects also match, are identical to each other. Effectively, you want to achieve some kind of a binary decision, yes or no kind of a decision. And the physical cryptography that we are pursuing can be seen similar to zero-knowledge proof, which was developed in the late 80s in the field of information theory. And it essentially has three criteria. First one is soundness, which you can think of it as type 1 error. So a cheating approval will be called. You have a significant detection probability. Completeness, which means that the honest prover will be cleared. You will not raise alarm if it's an honest device. And finally, the zero knowledge is that if the prover honest, only if the prover is honest, the verifier will learn nothing additional. So just to be clear, I'm using different terms here. Prover, verifier, it means host and inspectors. Hosts are proving, the inspectors are verifying. So the hosts are the provers, the inspectors are the verifiers. All right, so the problem at hand is that prove that weapons A and B are identical without revealing any additional information about the warhead. Okay. So what's this mysterious physical process? What can be a physical process that satisfies these conditions? So last month you heard about neutron transmission radiography, which is something that the Princeton team is pursuing. And we are pursuing a method which is based on transmission nuclear resonance fluorescence, transmission NRF. Okay, so now that we have gone through the general high-level structure of the process, let's talk about NRF. What is NRF? So one way to think about NRF is to think about optical spectroscopy. So think about atoms. Forget about nuclei. One way to get the atoms to emit photons, optical photons, because it is on an optical scale, okay, is to heat them up. Okay, so like black body radiation, you have incandescent filament inside a light bulb, or you have the surface of the sun. There are approximately black bodies, and they will emit a continuous spectrum, which will be, in case of white light, is uniformly from ultraviolet to infrared. Alternatively, instead of using black body radiation, you can cause excitations inside some kind of a gas, either by heating it up or passing current through it. So you can think of like neon lights. That's what neon lights are. You're passing current through them. The electrons, they interact with the electrons, orbital electrons, and then kick up the atoms to excited states. Okay, so atoms are effectively quantum systems which have ground state, excited state, second excited, third excited state. And if you do things just right, you can get the atom to transition, the orbital electron transition from the ground state to the excited states and back down. When they decay back down, they emit optical photons, which are whose energy is equal to the difference between the excited state, which they got to, and the ground state. So you will get basically an emission spectrum. You will get photons of very specific colors and energies. Alternatively, what you can do is that you can take a continuous flux of photons, okay, for example, black body radiation, and you can shoot it through cold gas. Okay, so in that case, you'll have an absorption spectrum because the photons that correspond to these energies will get remitted into 4-pi, and you'll see very few of them downstream. So, for example, the emission, this emission spectrum, this is what you use for doing elemental analysis from certain planets, or for a proton spectrum to, let's say, look for the optical light of a star and which lines are missing.
Areg, I'm getting a lot of static on the line, and I'm wondering whether something just happened to your microphone.
Okay.
Unfortunately, it's really distorted.
I see. Should we try
Did anything happen on your end?
Not really, other than maybe my hands. Should we try the phone? Okay. My phone number is it's 617.
Well, you'll have to. I think what you'll need to do is to log out and log back in. And
okay.
Now wait a minute. Now you're fine again. Something was happening, but it seems to have gone past now.
I see.
Okay.
Let me just.
Yeah, go ahead.
I'm trying to turn off anything that might be producing some noise here, like some device. All right. If it comes up again, let me know, and we'll try what you said.
Okay. Seems fine now. So.
Okay. All right. Okay. I'll try not to touch the microphone.
Sorry about that.
Yeah, no problem. So just to repeat what I was saying, if you heat up the gas or you pass current through it, you'll get emission spectrum. If you take optical light and shine it through the cold gas and do spectroscopy, you'll see an absorption spectrum. Okay. So I have a little diagram over here. You can think of it as a ground state, and you are exciting the atom or the nucleus, which is I'll talk next about, to some excited state and back down. And for that, you require photons of specific energy, and photons of specific energies are emitted afterwards. So the equivalent to imagine what NRF is about, the analog of the black body radiation is Bremsstrahlung. So Bremsstrahlung is where you take an electron beam, you impinge it on, say, metal targets. The electrons undergo rapid deceleration in the Coulomb field of the nucleus, and every time you take a charge and rapidly, decelerate it, they emit photons. So one example is the electrons in your cell phone's antenna. As you are moving up and down, they emit photons of very, very, very low energies. When it comes to the nuclear Coulomb field, the deceleration is much more dramatic, and the photons are emitted for an MEV electron, they'll be emitted on MEV scale. So you end up having this like approximately 1 over E type of distribution. The equivalent of the emission spectrum is backscattered NRF. If you take MEV photons and shine them on some nucleus, you can get a nucleus to undergo transition from its ground state to its excited state. Okay, and thus photons of specific energies will be emitted as a result of that. Now, unlike say atomic spectroscopy, something that determines which photons will actually get to do this, because what I said a bit earlier was that the photons have to have the energy that is equal to difference. Well, question is about how equal. Okay, how equal is equal? So for NRF, actually, in the center of mass frame for the nucleus, the width of these lines is something like tens of milli-electron volts, while the energies of the lines themselves are MEVs. So we're talking about 8 orders of magnitude of difference between the energy of the photon and the width of its energy, which is acceptable to trigger the transition. Okay. In real life, if you do actual measurements, so this is an actual data collected by a team at Passport Systems, okay, for mix of uranium, doing on NRF on uranium-225, the actual widths are going to be keVs, and this is because the detector's resolution is highly limited. Okay, it's only at the keV. We can never do the measurements at electron volt scale. So, but to add an additional technical detail, is that while the widths are tens of milli-electron volts, they actually get broadened quite a bit because the nuclei are moving around. So you get Doppler broadening, just like you have emergency car moving, driving past, its sound is changing. Similar for nuclei, there'll be a broadening in the energies from tens of milli-electron volts to electron volts, okay, which is still too narrow for our detectors to resolve. So we see something that are kilo-electron volts wide. Okay? So the equivalent of the absorption spectrum is if you look at the downstream, you take, let's say, uniformly distributed photons in energy, and you look downstream, you'll see this very thin absorption lines. By C, I mean they will be there. Now, the width, as I mentioned, are only electron volts wide, so modern detection techniques will never be able to infer that. However, there's something else you can do, which is, I will show it in the next slide, is you can put a foil where the photons that survive this will trigger secondary NRF from the foil. Okay? And from there, you can get a signal which is sensitive to the foil thickness and the original object's thickness. But the takeaway from this slide is that while atomic spectroscopy, optical spectroscopy, gives you essentially like an elemental fingerprint of the material, NRF gives you a unique fingerprint of the isotopics. Really, this combination of the lines ends up being some kind of a fingerprint of the isotopics. So you can sort of see where we're going. We want to have something that is very sensitive to the isotopics that the bomb is made out of. All right. So let's look at what the system is going to be made of. Okay, how does all these things come together? Template verification, NRF, how does all this fit together? So the general concept is the following. You start off with a Bremsstrahlung beam. Think of Bremsstrahlung as essentially continuous energy distribution well below and well above the NRF resonances. Okay, and this Bremsstrahlung goes through the weapon, and the transmitted beam will be NRF filtered. Okay, so you'll have these narrow absorption lines or notches. Then what you have got a foil of some kind of materials, and the photons that will survive in those absorption lines will trigger NRF inside the foil. And then you can have some kind of a detector, which here is labeled HPG, stands for high purity germanium detector. So just think of this as a detector, which can measure the photons' energy after they have been emitted in the backward direction. But the important thing is that this detector cannot see anything from the weapon itself, because there's dense, heavy shielding in between. They can never see anything from the foil. So the detector is only sensitive to some kind of a mix or convolution between what's happening inside the warhead and what's happening inside the foil. Now, it's kind of important to understand the the protocol, who does what, who has what, who brings what. Okay, so everything above this dotted line is classified by the host. Everything below the dotted line is open to everyone. So the hosts provide the candidate warheads, okay, which has to be authenticated. Okay, they make and provide the foil. The foil thickness is unknown to the inspectors. Only hosts know what the thickness is. But the isotopics of it, so which isotopes they're going to put in, are agreed upon. So, for example, you'll agree upon saying, we care about uranium and plutonium, make sure that there's uranium and plutonium inside the foil. How thick you want to make it, it's your business. But the hosts have to make the foil with some amount of uranium and plutonium. The inspectors bring the detectors and the electronics, which can be verified by the host if the host wishes to, and they need to have visual access to the foil. So even though the foil is in the classified area, so to speak, the inspectors have visual access to the foil, and they make sure that nobody is moving the foil around. Once the foil is there, it stays there. Okay. And as far as the two parties are concerned, they get hold of the golden copy. They do this joint exercise where they go, they randomly pick an ICBM, pick the reentry vehicle, and bring it and use that as a golden copy. Okay. All right, so how does this work then? So the concept is that you achieve physical cryptography by the fact that when you do a measurement of these things, okay, your final signal is going to be a convolution of the weapons makeup and the foil's makeup. Okay. So because of that, because you don't know what the weapon is made out of, you don't know what the foil is made out of, okay, from the signal it's impossible, or it's very hard at least, to infer what the weapon is made out of. Okay. So what you do is you do one measurement based on the authenticated template, the golden copy, if you will. Okay, and you get a spectrum. So here's a continuum. This is a simulated continuum with a few NRF resonances on top of that. Okay, this little peaks over here with error bars on them are the NRF lines that correspond to the resonances inside the nuclei. Then what you do is the following. You switch from the weapon A, which is authenticated template, to weapon B, which is a candidate that now you're trying to validate and authenticate. Okay, and you essentially do the same process all over again, same measurement times. You acquire the data, and now you do a spectral comparison. Now, if the spectra match, and if the foil was kept in its place, then the weapons have to be identical as well. One way to think about this is people who use cryptography in their daily lives, we do, for example, checksums only files. You download a file, say an operating system's image or something like that, and the website where you're getting it from has the hash based on some kind of MD5 sum or something like that of the file itself. And when you download, okay, you run the same algorithm, and you compare the hashes to see if they match. The idea being is that when you run the checksum or the MD5 sum, okay, you get a hash from which it's impossible to infer the makeup of the file itself. Okay. However, if you have two files, and if they produce the same hash, then it means that the files are the same as well. And still, you cannot infer anything about the file itself. But you do know that two files are the same. So you can think of the weapon as the file, the process inside the foil as the checksum, and the data inside the detector as the hash itself. Now, I did mention that, we have this convolution between weapons and the foil. It's actually the first order. You can calculate it. It's not too difficult. This is the simple formula where the first part in the formula is your counts, okay, your signal, your counts at a particular energy. Okay. The second part is exponential over here is essentially just the attenuation inside the weapon itself. And D over here is the classified thickness of the weapon. You don't want to find that. And finally, this big bracket over here takes account of what's happening inside the foil itself. Okay. And X is the thickness of the foil for a particular isotope. This is like really the simplified case. But one way, you don't have to go into the details as to what mu and everything else is, but one way to think about this is one equation with two unknowns, or multiple unknowns. You can also have unknowns in the Bremsstrahlung that's incident upon this whole assembly. Okay. So you have one measurement with multiple unknowns, and you cannot infer the individual unknowns if you have one equation with multiple unknowns. I mean, think about just high school math. Yeah. If A plus B is equal to 0, just because that is no, it's equal to 0, you cannot infer what A or B are. Okay, unless you do an independent measurement of that. Right. Okay, so how do we go about showing? So I talked about the general idea. I talked about some kind of a very schematic scale as to how this works. I talked about how we achieve information security, this is cryptography. Question of all, how do we know that this actually works? How do we know that we can tell the difference between, say, we can detect a hoaxing scenario? Okay, so we don't have nuclear weapons laying around MIT, fortunately or unfortunately, but something that you can do as a physicist, if you know the physics processes, which you do, you know NRF, you know electromagnetic processes, the MEV. The MEV physics is very well known, okay, overall. Okay, then you can do something that's called simulations. You can run Monte Carlos, where you can effectively simulate the way the nature works. Okay. So you can use existing simulation packages. In this case, we use the Gen4. It's an object-oriented simulation toolkit, originally developed for high-energy physics, and now it's being used in medium-energy physics, low-energy physics, in medical research, astrophysics, etc., etc. And we can essentially simulate this process. So we don't know what the weapon is made out of because we don't work behind the fence. But what we have done is that we have gotten hold of some approximate geometries available in the open literature, based on a measurement that was done during the famous Black Sea experiment in the 80s, where the Americans went to Russia and were allowed to take spectroscopic data off of naval anti-ship thermonuclear warheads. And then from the spectra, we're able to infer some approximate kind of parameters about the weapon's makeup. So we have this kind of a, if you will, cartoon bomb, which inside has a plutonium pit made out of weapons-grade plutonium. The green over here is the explosive. And outside blue is a HEU shell that it's covered with. And then we use a foil which is made out of uranium-235, 238, 239, and 240. Plutonium-239, plutonium-240. We run simulations where we shoot Bremsstrahlung photons of this, and we do measurements off of the foil itself. In the simulation, we run the simulations on Amazon Web Services cluster, EC2 cluster, which allows common people access to thousands of cores simultaneously. It's an incredibly powerful tool. So we use for most of our simulations, primarily for computational power, we use the pencil Bremsstrahlung beam, and we tried a few set of hoaxing scenarios where we try to replace different parts of the material with what we thought were reasonable hoaxing attempts. Okay, what someone would try to do, and then we ask ourselves, well, can we detect this scenario? Can we detect the difference, okay, between the null hypothesis with more than 5 sigma confidence? Okay, so and I'll show a few examples. So here's one example of a simulation where we're shooting 2.7 MeV Bremsstrahlung beam through this assembly, and we're looking at the back emitted photons. So first of all, what you see is this long continuum due to secondary Bremsstrahlung emission in the backward direction. And all this, what look like dots, are effectively the NRF lines. They correspond to resonances in some of the 4 isotopes which we included in our simulation. Sometimes correspond to uranium-238, sometimes correspond to uranium-235, and others yet correspond to plutonium-239, plutonium-240. Okay. So in this simple case, we have simply template versus an authentic candidate. Of course, they're going to match because of the simulation. Then we try the first thing, which is we replace the weapons-grade plutonium, which the weapons-grade plutonium pit is highly valuable. Okay, that's something the host might want to essentially, divert away. And we replace it with a depleted uranium pit of the same geometry. And then we ask ourselves, well, what will be the measurement? Like, how will they compare? So again, black is the golden copy and the red is the candidate. So this is what it looks like. So I want you to look at the difference between red and black. So you start immediately seeing very large discrepancies between the various NRF lines. Okay. You see at least 10, 20, 30 sigma discrepancies for every single line that corresponds to plutonium-239, plutonium-240, and uranium-238, because those are the ones that you change. For example, you can see a very good agreement over here, which is not surprising because the lines correspond to uranium-235, which has not been changed. But you also see, a slight change in the slope or the shape of the continuum. And this is not surprising because you have effectively changed the Z of the weapon slightly. And this continuum does have some sensitivities to the average Z of the weapon itself. All right, so we did a number of other checks as well. We did not limit ourselves to the simple check of weapons-grade plutonium versus DU. DU, just to clarify, is a commonly available material. You can almost buy it on the street, almost. We tried a few other scenarios. So for your weapons-grade plutonium versus DU check, we found that we can show 127 sigma discrepancy. Okay. We tried some other scenarios. For example, replacement of weapons-grade plutonium with the more commonly available reactor-grade plutonium. Okay. And even then, where this is like very, just for people who are maybe not in this field, the difference between weapons-grade and reactor-grade is only 10% difference in plutonium-239 concentration. Okay. And even then, where there's such a faint difference, we see a 7 sigma discrepancy. So 7 sigma, what does 7 sigma mean? It means that the probability that the difference was caused by statistical fluctuations is something like, I don't remember off the top of my head, is 1 part per 100 million. Okay. So if you see a discrepancy, you can reject that scenario. You can reject this candidate with that confidence, basically 100% confidence. What we also did was we actually tried various kind of geometric hoaxes. Remember, we're using basically kind of like an approximation of a conical beam. We are doing a pencil beam, okay? So we systematically tried to find a scenario where the isotopics along the line of sight of the beam was the same, but let's say the geometry was different. Earlier I had shown, I'm just going to jump back very quickly. So this is our weapon, and this is the geometric hoax. So we are going after both isotopic hoaxes and geometric hoaxes, okay? And we specifically found one which will match the spectral data if you were to do it like this. But we showed that if you take that geometric hoax and rotate it by just 10 degrees, you'll have something like a 9 sigma discrepancy. You go to 30 degrees, you get something like 80 sigma discrepancy. So effectively the way we approach this is to exclude geometric hoaxes. We simply take the weapon and we choose its orientation randomly. And maybe we do a few different measurements. The probability that the beam will line perfectly with that perfect axis, okay, of the previous image is extremely small. Since I talked a little bit about that, a few words about geometries and tomography. So this is the part of the project which is led by Scott Kemp and Rory McDonald, who are our collaborators. Okay, so effectively our transmission NRF system is, you can think of it as a single pixel camera. Okay, and the real question is that can you come up with complex geometries which nevertheless will go unnoticed? Okay? And the general takeaway over here is that yes, it's possible. However, in order to describe that geometry, you can describe it in terms of Zernicke polynomials of a particular order. And for a particular order and particular set of measurements and a particular type of angle resolution, you can calculate the probability of a specific type of a geometry slipping through unnoticed. Okay. So we found out, for example, for an object that is Zernicke polynomial order of 60, will effectively fetch a probability is close to 0. But look what that looks like. So this is a Zernicke polynomial order of 60. It's a lot harder to manufacture this object than to manufacture a simple kit. So geometric hoaxes are possible, but they are too complex to be of any value to the hosts. Okay. So since I'm starting to run out of time, very briefly about our future plans. We are not doing only simulations, we're also doing experimentations. We're using the MIT's high voltage research laboratory which provides 2.5 MeV electron beams, so we can make Bremsstrahlung. We're planning to build a proof of concept system. We also plan to use it to validate our simulations further, which would allow us more broad confidence in terms of trying various kind of hoaxing scenarios and better understanding various aspects of this system. Last summer we did measurements precisely to acquire data to do validation of the code, but we also plan to use this facility for building a proof of concept systems. This is just 2 words about that. This is using the Van der Graaf machine, the same Van der Graaf machine that you saw in your high school class, except much bigger, much larger, and on megavolt scale. So it can produce potential drops of something like up to 3 megavolts, which will accelerate electrons. This facility is famous that Van der Graaf himself used to apparently work there in the 60s. It's apparently that old. There's another facility in Santa Barbara, which is also a Van de Graaff machine. It's a Pelletron, okay, which goes up to 5.5 MeV. Right? Few just very quick things about the data that which required. We took data with aluminum, with uranium-238, just TU, and we were able to observe all the NRF resonances, relevant ones anyway. You will notice that you see these three major resonances, and there's this kind of like twins, or they're siblings, so to speak. They have to do with the fact that you excite the nucleus to an excited state, and then from the excited state, you may sometimes decay either to the ground state or to the first excited state, which is at 45 keV. So you end up having two photons, one at the full energy of the excited state, and one with minus 45 keV. Just to wrap up about conclusions, I would say that this is perhaps the first isotope-sensitive physical cryptographic technique concept. Okay, our Monte Carlo simulations for fairly simplified warhead geometry indicate that with realistic detector geometries and with realistic beams that are available today, we could probably achieve detection in something like 10 minutes or less. Okay? However, additional studies are necessary to understand the full phase space of various kind of possible hoaxes. Okay, we do plan to build a proof of concept experiment using surrogate materials, and also the information security is a big topic. So we need to further understand the information content of the observed data. Is there something, I gave you a certain first order description of what's happening, but there may be some additional things that we'll have to worry about. Again, to mention, if you know of anyone who's interested in the Stanton Fellowship, this is the website to go to. And with that said, I am ready for your questions.
Okay, thank you. So let me just remind people, you can either, if you have a question, either send it to the chat feature or to the Q&A feature up here. I wanted to start with two questions. One is, when you were talking about the unknowns, you were mainly talking about the thickness of the foil, but the isotopic content of the foil is important as well, isn't that right? So you actually have
absolutely, yes.
So you actually have quite a few unknowns, which helps you believe that you're not going to be able to deconvolute those signals.
So the important thing is that, let me try to tell me if I'm able to answer this, if I'm answering the question or not. One question that people do raise a lot relative to that is, well, how do they know that they actually put uranium-238 and they did not put, say, iron or something like that? The answer is that the data is self-validating. You have to see NRF lines that correspond to uranium-235. So you tell the host, say, I don't know what you do, but I better see lines for uranium-235. The simple analysis I showed over here is, yes, it's only for just one element. So in reality, it's more than that. That's absolutely true. Does this answer the question?
But doesn't the amount of the different isotopics matter, because that will change the peak heights, or do you not care about that? Is it just the positions?
Absolutely, no, absolutely. So this formula that I have, X is the thickness, the effective thickness of particular isotope inside the foil. Okay, and the notion is that only the hosts know it. So the inspector, I'm the inspector, right? I do not know what X is. All I know is that there is isotopes for uranium-238 or uranium-235, but I don't know what the thickness is, which is what prevents me from determining D based on a measurement of, of the counts of particular energy.
Right, but so you actually, I think the example you showed later, you had 4 different isotopes that you were talking about. So you'd actually have 4 different X's here. Is that right? Because that would vary for each isotope. Yeah.
So you have 4 sets. In this specific example, you have a set of 4 X's and 4 D's and 4 Phi's, and they are independent from each other.
Right. Right.
So each one of them is an equation, multiple unknowns. One equation, multiple unknowns. They cannot use them against each other.
Right. The other question I had was it just to ask you the sort of general question of how you see, what advantages you see of this methodology over the method we saw last month from the Princeton group?
That's right. So let me start with the advantage of the Princeton group. The advantage of the Princeton group is that they truly aim for zero knowledge. They really effectively, their final signal is basically flat with possible noise on that. That's as close to zero knowledge as I think you can get. That's a really significant strength. The trouble with neutron transmission, especially at the MeV scale, is that if you go look up the cross sections for neutron interactions at 14 MeV, which is what they had in their discussion, they are essentially identical between plutonium-239, plutonium-240, uranium-235, uranium-238, thorium, etc., etc., etc. So someone can replace, say, plutonium with depleted uranium, for example, and their technique would not be able to see it. Now, they can mitigate it by measuring neutrons sideways, but that makes it quite a bit difficult. The main strength, main advantage of our technique is that we, as I mentioned earlier, we really get like an isotopic fingerprint of the object of the weapon. So any changes to the isotopics immediately result in big signals, big differences, which is something that's very hard to do with neutrals.
Okay. Frederick has a question. Let me just unmute you here. Go ahead. Frederick?
Sorry, I muted my telephone. In your scenario, you assume that it will be possible to transport the nuclear weapons to a venue where there is a Van de Graaff accelerator available. Is that correct? Because the accelerator will not be portable.
So that's right. So notion being is you have got a crew which is made out of the inspectors and the hosts. They go to an accident site. They pick the warhead, and then the warhead is in a joint custody, what's called joint custody, and they together move to the facility where this verification will occur. Right. So you don't move the verification facility to the ICBM. You move the warhead, but that's fairly doable. So.
Let me just unmute you again. We're getting some feedback. Did you have a follow-on question, Frederick?
Yes, please. I agree, but I talked to other people who are actually do not consider it realistic that the nuclear weapons will be moved to a special venue, but rather propose that the verification has to take place in the disassembly facilities which are already existing or will be in places where access will be very difficult. But thank you for your answer.
Right.
Okay.
No, that's right. The notion is that maybe I wasn't clear. The verification, this whole facility will be built will be put together at the disassembly facility, at the facility where disassembly is occurring. We're not talking about huge accelerators. We're talking about relatively compact, things that can be put together where the surplus weapons are located at. I thought your question was about the template, about moving the template from the ICBM to the verification facility, which I think that's doable. I mean, lots of these questions are also about political will, right? Some things that seem to be kind of unrealistic, you find out, well, when there's a political will, they'll do it.
Any other questions?
Mm-hmm.
I don't see any coming in. Thank you very much for this. This is really interesting to see how you're approaching this. The recording of this will be put up hopefully. Oh, wait a minute. Frederick looks like he has another question. Go ahead.
Yes,
go ahead.
Muted, so you couldn't hear me. I have one more question, which is right now your simulations, which you showed at least, do not consider external shielding. Did you think about that? Did you make more simulations, or do you think that it won't be necessary? Because actually, if I have the warhead, then I also might have some depleted uranium surrounding the whole weapons pit.
So again, we have limited amount of information of what the weapon is made out of. If the measurement, in principle, measurement can be done at different stages of disassembly. You could do this at a fully assembled MIRV, right? So on this picture, we have the actual, the re-entry vehicle itself. But of course, yes, if there is, like I say, additional shielding inside, then you have to be able to shoot through that. So your measurement times will be probably longer, and either that or the necessary beam intensities will be higher, which is, I think, still feasible. You could also posit that some of these measurements can be done, say, after one step of disassembly, where, let's say, the MIRV is brought in, the physics package is pulled out, then you do these measurements on the physics packages themselves. Or depending what various kind of constraints are, you might even perform these measurements at a slightly later stage of disassembly. Obviously, the more disassembled the weapon is, the faster and easier it is to do the measurement. The only question is that you have to keep track of this whole process, make sure that nothing, insidious has been introduced into the assembly.
You may have answered this, but it's not completely clear to me. I think the question was, what if you add something that's not just shielding that makes the times longer? You actually add something that adds a different signal, like a depleted uranium wrap around it. Does that give you problems in this? So
you mean so this is black thing? So this black thing that says shielding.
Right.
Yeah.
So the signal you got from the warhead would now be the warhead plus whatever the shielding is.
That's right. So the idea is can the host effectively try to kind of complicate your life by say adding some kind of depleted uranium, and the idea is that the passive signatures from depleted uranium are fairly small, and I think they're because we're using fairly intense beam with intense rates. That's probably not going to be a big contributor. However, what you can do is that you can, in principle, perform, if you will, a validation of the facility before the beam is turned on. You can put your detector over here, and before the beam is turned on, you can acquire some amount, so even before the foil and the weapon have been introduced, you can take some data of this shielding, and you can verify that there is nothing that's, irradiating your detector and is confusing your system.
Yeah, I guess the other way to say it is that the person who's bringing the warheads has an incentive to be able to prove that the warheads. I mean, in other words, if the person giving you the warhead has done something that keeps you from being able to validate warheads at all, then the whole system doesn't make any sense, right? So there was
that's right. So.
Yeah, there's a question from Mark. Let me unmute you. I don't know if you got the answer you needed, but go ahead if you want to ask it.
Well, I was just wondering if this could be combined with, say, by spatially patterning the foil, or is there a way to add a geometric signature? Scott noted that the random orientation does that to some extent already, but I just wondered if there's a reason why this is restricted to an unpatterned beam.
So do I understand correctly whether the host could use a patterned beam or a patterned foil to effectively to hoax, to spoof you, or whether that could be, is that the question?
No, whether the method could be strengthened by adding some kind of spatial patterning, something similar to the Princeton method.
So something we did consider in the past is, and you may have to do this, is the foil may have to be basically patterned, and the inspectors, this is more detailed maybe than is necessary, the inspectors will have to choose like a random section of a bigger foil. Because in principle, what can happen is that when it comes to spatial kind of distributions, the hosts may specifically optimize a foil so that the signal is not really sensitive to how much plutonium there is inside the weapon. That is overcomable by taking a random spot inside the foil. In terms of can we raster the beam, or that's also, I mean, angular measurements, if you are rotating randomly, picking the direction of the warhead. Scott is right. That essentially does some of this. It gives you sensitivity to the three-dimensional nature of the weapon itself.
Okay, we are at 1 o'clock, sort of out of time. Thank you very much for this. It was a very clear presentation. I think it gave people a very good idea of what you're doing and why. As I said, this will be recording up on the web if you want to see it again, or pass it on to people who weren't here. And thank you again for joining us today.
Yep, the pleasure is mine, and I was very glad to be able to do this.
All right, thanks very much.
Thank you, everyone.